The next topic in our physics section of the course is work and energy. Let's start our chapter with a conceptual question. We all have seen this pendulum swinging back and forth, and our question is, when you release the pendulum ball, it swings back to the same position after each swing, and so we want to know what causes this back and forth motion of the pendulum. And the answer to this question is, when we initially raise this pendulum by some height, we have to apply a force to move the object against gravity, and when we apply this force, the force does some work on the pendulum, and when we release this force, when we raise this ball, we change the energy level of this pendulum ball, and when we release this pendulum, the energy is converted from one form to another form, and this change in energy causes the motion of this pendulum. We will talk more about this change in energy and what kind of energy are involved in later in this presentation. And before we define work, we need to remember how we define force. We define force as a tendency to push or pull, and then we also know that force can cause a change in motion. We talked about that in Newton's law of motion, and if the force can cause change in motion, that means when we apply force, we may have a displacement. And now we can define this work in terms of force and displacement. So the work done on object is defined in terms of force and displacement. It is the product of the force applied times the displacement caused by the force. Here we can see in the example, the initial position of the object is here, and then the person applies some force F and moves this object from the initial position to some final position here, and the displacement of this motion is d, represented here. And if we want to calculate the work done by this force F on this object here, the work done is force time displacement, and the unit is the force is Newton and displacement is meter, so the unit of work done is Newton meter, and in other word we also call it joule, and joule is generally written as capital J, and 1 Newton meter is basically 1 joule. And the dimension of work done is mass times length, length square over t square. So if you have forgotten what dimension is physical quantities, fundamental physical quantities. So dimension is basically the fundamental physical quantity that makes up that physical quantities. So work done is made up of mass, length squared over time squared. Now let's look at how when is work done. If we have several force, what what kind of forces will do work and what kind of forces will not perform any work. In order for a force to do a work, the direction of the motion or the direction of the displacement should be parallel to the force applied. Here we can see in the example, here in the diagram, we have two forces, F1 and F2. F1 is moving in this horizontal direction, sorry, F1 force is oriented in this horizontal direction, F2 force is oriented in vertical direction. And if we see the final, so this is initial position, this is final position, we can see that the object is still in the ground, meaning it's not moving up and down, so the force F2 is not doing any work. And if you see here, the force F1 moved the object in horizontal direction, so this force did some work on the object, and the work done is F1 times perpendicular, sorry, the distance displacement here. So we should probably just define it as displacement rather than distance, since the work done is a vector quantity. It's better to define as a displacement rather than distance. And one more thing is that work done can be positive as well as negative. We will talk about that in next slide. Before that, let's see an example. A toy car is pushed by a force of 50 Newton for 0.4 meter. What is the work done? And work done is defined as force times displacement. For the force applied on the car is 50 Newton, and the displacement of the car is 0.4 meter, and the product of force and displacement is 20 Newton meter. In other words, work done is 20 joule. And the second part is if the amount of work done on the car is 20 joule. Now in this section, instead of force, we are given work done while the car moved a distance, and distance is also given. Under a force, what is the force acting on the car, and it's asking us to calculate the force. So we know work done is force times distance, so force is equals to work done over distance. And if we substitute these numbers, 20 joule over 0.8 meter is 25 Newton. So the force applied on the car is 25 Newton. Now let's look at one more example here. A common misconception is that holding an object still requires work. Here we can see this person is holding a briefcase, and we know that in order to hold the briefcase we have to apply some load. However, if you look at the briefcase, the vertical position of this briefcase is a constant. It's not moving up and down. So if you are just holding the briefcase, you are not doing any work. Suppose a person is still holding a briefcase as shown in the figure on the left, and clearly a force is exerted on the briefcase, and the force applied on this briefcase, in order to hold it at the position here, you have to apply the force that is equal to the weight of the briefcase, right? If the weight of the briefcase is 20 Newton, then you have to apply a force of 20 Newton to hold it at this position. And since it's not moving, there's no displacement, so there's no work done. And since the distance moved, the direction of the force is zero, no work is done. However, if you look at the initial position, when he picked this briefcase from the ground, he moved the briefcase by some distance in the direction of the force. So he did some work initially when he lifted the briefcase from the ground to this position. Now let's talk about kinetic energy. Before talking about kinetic energy, we need to know what is energy. Energy is defined as the measure of the ability to do work. In order to do work, you have to have energy, and energy, like we said, for a pendulum can cause a motion, and the energy due to motion is called kinetic energy. Energy due to motion is called kinetic energy, and mathematically it's defined as kinetic energy is half mv square, where m is the mass of the object, v is the velocity, and the unit of energy is also Newton meter or joule. And we just defined the kinetic energy as energy due to motion. So if an object is at rest, that means there's no kinetic energy, because the velocity of the object is zero. And if velocity is zero, then kinetic energy is zero. In the second case, we have some force, and this force is causing motion, and the object has some velocity v. Then the kinetic energy is given by mass times half m v squared. And let's look at the relationship between work and kinetic energy. This is sometimes also called work energy principle. The key relationship between work and energy is that work done is equal to change in kinetic energy. The work done on an object can change the motion of an object, and it can either speed up the motion or it can slow down the motion. And if the work is increasing the motion, then the work done is positive. Positive work done increases motion, and negative work done slows down motion. And in other words, we can also say that if the work done, if the force and motion are in same direction, then the work done is positive. And if force, displacement, and if the work done and the motion are in opposite direction, if the force applied and the motion are in opposite direction, then work done is negative. So what this means is when we are doing work, on an object, we are changing the energy level on the object, energy on the object. And if we want to define the work in terms of energy, the work done on an object is equal to the change in kinetic energy, because the work done on the object is basically used to change the energy. And we can expand this work done is equals to change in kinetic energy furthermore. And if we look at here, change in kinetic energy is equals to final kinetic energy minus initial kinetic energy. If the final velocity is v2, then half mv2 squared, and if initial velocity is v1, then the overall relation change in kinetic energy is half mv2 squared minus half mv1 squared. And by definition, this change in kinetic energy is the work. And if the object starts from rest, meaning the initial velocity is 0, and then the work done is half m v2 squared, because the initial velocity is 0, we only have a final velocity term. And if the object is brought to rest, then the final velocity will be 0, meaning the work done is negative, because the motion is reducing from some velocity to 0 velocity, and it's given by half m v1 squared, because v2 is 0, change in kinetic energy is just given by the negative of initial kinetic energy. Let's look at an example of force. Force is given 20 Newton, acts on a toy car of 0.4 kilogram. So mass is given 0.4 kilogram, and distance d is 0.6 meter. And it also mentions that the car is initially at rest, meaning v1 is equals to 0. And we want to calculate in the first case, we want to calculate work done. Work done is equals to force times distance. Force is 20 Newton, distance is 0.6 meter, this is 12 Newton meter, or we can also write it as 12 joule. And the second question is asking what is the final kinetic energy. And just before this slide, we said that work done is equals to change in kinetic energy, and change in kinetic energy is final kinetic energy minus initial kinetic energy. And in this problem it says the car started from initial position, meaning v1 is equals to 0, so the final kinetic energy is equals to work done, because this part, the initial kinetic energy is 0, so this final kinetic energy and work done are the same. So we can say work done is equals to final kinetic energy, therefore kinetic energy is equals to 12 joule. And the third part of the question is asking us to calculate final velocity. And now we know what is final kinetic energy. If we know the kinetic energy, we also know the relationship between kinetic energy and velocity, which is kinetic energy is equals to half mv squared. If we isolate velocity, what will we get? Velocity squared is equals to 2 times kinetic energy over mass. And then if we want to calculate this value of v, and we have to remove this square, so squaring both sides, taking square root on both sides. What do we get? We get B is equals to root over 2 times kinetic energy over m, and this is square root 2 times kinetic energy is 12 joule over mass is 0.4, and if you calculate this, your answer will be 7.75 meter per second. So using the work done and kinetic energy, we can calculate the final velocity of the of an object. Now let's talk about potential energy. Potential energy is a measure. This is a wrong slide. We will talk about the potential energy in next slide. Next video.